Okay, in this video we're going to go through the final exam review packet. I'm going to try to keep a running number up in the corner so you can kind of skip ahead if you need to get to a specific problem. I have a written copy of the answer key that I made. It's already up online so you can check that. Here we go. So a lot of these I'm just going to kind of talk through. So number one, 3 examples of chemical and physical changes. Well, chemical changes are basically observed when when the composition of it is actually changing, when there's sort of a reaction taking place. So chemical changes include things like rusting, things like when something combusts, when something decomposes, when something synthesizes, when something burns, like if you take magnesium, burn it in a flame, it creates magnesium oxide. For physical changes, basically the chemical composition remains the same, so it's your obvious things like crumpling and cutting. It's things like melting, boiling, and the other phase changes. Really anything that doesn't change the composition. Dissolving something, that doesn't change the composition because you can basically remove the water and create the substance again. Okay, so that's plenty of examples. Number 2. Define each of the following terms. So an atom is the basic sort of particle of matter. It's the smallest unit that can't really be broken except by extraordinary means through nuclear fusion or fission. The molecule is a term for a group of atoms that are covalently bonded. We kind of throw the term molecule around a little loosely. Technically it means covalently bonded atoms. So things like N2, that's a molecule. Element is one of the 110-ish substances. It can't really be broken into anything simpler. Once you have an element, you can break it in half, and break it in half, and break it in half, but it's still going to be that same element. And a compound is 2 or more different elements. So N2, as I mentioned before, is a molecule, but it's not a compound. Something like NaCl is a compound, CCl4 is a compound, H2O is a compound. Okay. Number 3. What formula is used to define density? Density equals mass over volume. I like to think of the density fox with weird eyes to the side there. Mass over volume. That little symbol that we set up, the triangle, goes D MV. Those of you who are driving now know it's a mountain of paperwork to climb over the mountain of the DMV. So density equals mass over volume. So with this, if you want to solve for mass, it's density times volume. If you want to solve for volume, mass over density. Best way to do it though, just keep an eye on your units. If your units don't cancel out right, you have the formula wrong. Number 4. What does the specific heat or specific heat capacity mean? Well, it's how much heat it takes something to warm up or cool down. And even more specifically, it's the number of joules it takes for 1 gram of a substance to increase or decrease by 1 degree Celsius. The way we know that is the unit. For example, for water, it's 4.18 joules per gram degree Celsius. That means for water, for every 1 gram of water to go 1 degree Celsius takes 4.18 joules. Number 5, the formula for Celsius to Kelvin. You take degrees Celsius, you add 273.15, and that gets you your Kelvin. Number 6, how many total atoms are represented by the formula Al2SO43? So that would be aluminum sulfate. Well, you just got to add them all up. So 3 relates to this, so that's 5 in there, so that's 15, 16, 17 total atoms. Just got to add them up. 2 aluminums, 3 sulfurs, 12 oxygens. Number 7, how many total ions? Well, same thing, we have Al2SO43. What you have to recognize is that this polyatomic ion always stays together. So we have 2 aluminum ions, like this, And then we have 3 sulfates for a total of 5 ions. Number 9. The name. Aluminum sulfate. Aluminum sulfate. Next one, value of Avogadro's number. That's number 9. 6.022 times 10 to the 23rd. I believe you get that on the exam. Number 10. What does that number mean? Well, it's basically the number used for a mole. I think the official definition is that's the number of particles in a mole. Or you could say it's the number of atoms in a mole of atoms, or the number of molecules in a mole of molecules. But it represents the number that corresponds to the mole. Number 11. What's the molecular weight or molar mass of magnesium hydroxide? This is a naming problem. You gotta know this. So for magnesium, we have 24.31. For oxygen, we have 2 oxygens, so it's 16.00 times 2, so that's 32.00. For hydrogens, it's 1.008 times 2, which gives me 2.016. Adding the 3 of these up, 24.31 plus 32 plus 2.016 equals 58.33, and my unit there is grams per mole. I just check on my answer key that my math is correct. Yep. Next, number 12. What is meant by the law of definite composition? Definite composition means when you have a particular compound, it's always going to have the exact same formula, meaning it's always going to have the same ratio. I like to say water is always H2O. It's not like water is an average of H2O, and some water is H3O and some is H1O. All water is H2O. All salt, table salt, is NaCl. All, oxygen gas is O2. So basically, if you have a certain substance, certain chemical, that's the formula that it's always going to be. Number 13. What is the percent composition of NaNO3? Well, for percent composition, we're looking for percent composition by mass. So, for Na, well, let's do NaNO3 first. We'll do the total. Basically, we're going to divide each of these elements by that total. So, NaNO3. I'm going to cheat and use my answer key, but basically, you find this on the periodic table, you find this on the periodic table, you do 3 oxygens, you add it all up, and what you get is 84.99 grams. Okay? Then what we do is we look up each individual element. So for sodium, on the periodic table, it's 22.99 grams. We divide that by our total here. Gram cancels gram. We're going to do times 100%, which gives me 27.05% Na. Next, N, nitrogen, 14.01 grams, divided by the total, 84.99 grams. Gram cancels gram. This gives us, times 100%, 16.48% N. And finally, oxygen. Here's my oxygen. So there are 3 of them. So I would do O times 3. So 16 times 3 is 48.00 grams, divided by my total 84.99 grams. Gram cancels gram. Gives me 56.48%. That's my answer. These should add up to about 100%. And by about, I mean like plus or minus 1%. So 56 plus 16, well, we got the halves here, so that would be 60, 72, 73. 73 plus 25, 100%. Number 14. What is the empirical formula for a compound that is 52.2% carbon, 13% hydrogen, 34.8% oxygen? Okay. Empirical formula. We're looking for the simplest ratio of the elements in this one. Now, if we're given percentage, we assume it equals 100 grams, and we're going to basically turn that into grams. So, if it has a mass of 100 grams and it's 52.2% carbon, we would assume 52.2% grams of carbon, and we're going to assume 13.0 grams of hydrogen, and we're going to assume 34.8 grams of oxygen. Again, I just turn the percentages into the grams here, assuming 100 grams. Okay. Now again, I'm just going to kind of cheat for the sake of time, but we should all know how to convert these to moles. What we're now going to do is convert these to moles and try to find the simplest mole ratio we can find. So for carbon, we multiply by 1 mole of carbon over 12.01 grams. For hydrogen, we're going to multiply by 1 mole of hydrogen over 1.008 grams. And for oxygen, 1 mole of O divided by 16.00 grams. And what we get is, gram cancels gram, 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 gram. We're left with moles. 4.35 moles of carbon. We get 5.92 grams, moles. I'm looking at the wrong answer. So yep, 12.90 moles of hydrogen, and we get 2.18 moles of oxygen. Now, if you can see the pattern, you can write your formula, but I can't really see, well, I can sort of tell what it's going to be because that seems to divide pretty evenly into that. But basically, if you can't see the formula, what you do is find whichever one is the smallest and divide all the numbers by that. And by doing that, you're going to basically say, turn the smallest one into 1 mole. So the smallest one here is 2.18. So I'm going to divide this by 2.18, and I'm going to divide this by 2.18. And obviously, if I divide that by 2.18, it becomes 1 mole of oxygen. So 4.35 divided by 2.18 gives me 2.00 moles of carbon. 12.90 divided by 2.18 gives me 5.92 moles of hydrogen, and we have our 1 mole of oxygen. Now, this 5.92, ideally I would like to see that a little closer to a whole number, but we're going to say that is close enough to call 6. So it becomes 2, 6, and 1. So I'm just going to rewrite my formula. C2H6O. Because I have 2 moles of carbon for every 6 moles of hydrogen for every 1 mole of oxygen. C2H6O. Number 15. Balance the equation. Ti, that's titanium, so this would be titanium 4 chloride plus water yields titanium 4 oxygen. That 4 refers to the charge on the titanium, plus hydrogen chloride, not hydrochloric acid because it doesn't say aqueous. Anyway, balancing this out. All right, titanium matches titanium. Let's see what I want to do. I'm seeing 4 chlorines, so let me try a 4 here. That gives me 4 hydrogen, so let me try a 2 here. 2 oxygen, easy. 1, 2, 1, 4. Okay. Number 16. What is the molecular formula of a compound if the empirical formula is CH2 and the molecular weight is 56 grams? Molecular weight, another way of saying molar mass. Okay. So what we do for this, we go from empirical to molecular. You're going to compare the empirical to the molecular, and you should see some kind of small whole number ratio. That tells you how many times you need to multiply the empirical formula by to get the actual formula. So what we do is we find the molar mass of CH2. So this is going to be 12.01. This is going to be 2.016. Added together, that's going to be 14.026. We'll call it 14.03. And we're going to divide that by the mass that's given to us in the problem. Okay, 56 grams. So that's the total weight divided by 14.03 grams. And we're going to basically look for the percentage. And again, it should be a small whole number ratio. I'm guessing it's, what is that, 4? 56 over 14.03 gives me 3.99. 2 sig figs gives me 4.0. What this tells me is that this molecule here, that empirical formula, is 4 times smaller than what it actually is in real life. Because the actual mass is 56. This mass is only 14. So what we do is we take CH2 and we're going to basically apply a factor of 4 to that. So it becomes C4H8. Number 17. Describe the relative mass and charge of the following. Okay, protons have a positive charge, neutrons have no charge, and electrons have a negative charge. Protons and neutrons are about the same size, and electrons are about 1,800 times smaller. 18. What is meant by the atomic number? It's a number of protons. It's also the way we define what element we're talking about. 19. What is meant by the mass number? Protons plus neutrons. 20. What does it mean if two atoms are isotopes? It means they have the same number of protons, or in other words, it's the same element, but they have a different number of neutrons. 21. Describe each of the following models. Dalton. Basically, atoms are solid spheres that can't really be broken up. The Thomson model, he figured out that there were small negative particles, so he created the plum pudding model, where we have these negative charges floating around in a sea of positive charge, because he knew the atoms themselves had no charge, so if there were electrons, the rest of the atom must be positively charged. Next model was Rutherford. He basically fired gold alpha particles through a gold foil, and he discovered a tiny positive center, so basically he discovered the nucleus. And he said, well, there are still electrons in there, so I'm going to assume they just kind of orbit around the nucleus like this. Okay? So basically with Rutherford, it's all about the nucleus, and Bohr said, well, it's not quite like this. In fact, we have the nucleus, and we have these set energy levels where electrons can exist. That's our Bohr model. Write the configuration of the first 20 elements on the periodic table. Did I do all these? I'm not going to do all 20. See if you can read that. I'll do a couple. I'll do a couple on the board, but I'm not going to do all 20. This is number 22. All right, I'll choose magnesium. So for magnesium, if you want to write it out with the arrows, we're going to say 1s with 2. And by the way I am looking at this, I basically look at my periodic table here, so if I can do this without dropping the computer. And this is my 1s2. This is my 2s2. Next is 2p6. This is 3s2. So because my magnesium ends at 3s2, I know that's where I'm going to end at. You could also just count from 12 and basically fill them all in. Okay? So I need to take care of 12, but I also know that I'm ending at 3s2. 1s. 2s gets 2. Next is 2p. So I'm going to do 2px, 2py, 2pz. 1, 2, 3, 4, 5, 6. Fill them this way. That's Hund's rule. And 3s, you get 2. That's magnesium. The other way we write this out is 1s2, 2s2, 2p6, 3s2. So there's two ways of writing it. Actually, the third way is noble gas notation. So we would trace this back to the previous noble gas, which is neon, and then we just tack on 3s2. So really there's 3 ways of writing this. I'll do one more. I'll do chlorine. Chlorine has 17 electrons, and looking up here, I can tell you already what it's going to be. 1s2, 2s2, 2p6, 3s2. Now I'm in my 3p's, and let me count down the line. 3p1, 3p2, 3, 4, 5. So it's 3p5. So I can tell you right now what the configuration is going to be based on the periodic table. 1s2, 2s2, 2p6, 3s2, 3p5. The way we write this out with the arrows is 1s2, 2s, 2px, 2py, 2pz, 1, 2, 3, 4, 5, 6. 3s gets 2, 3px, 3py, 3pz. Now, counting, I need 17, 2, 4, 6, 8, 10, 12, 5 more. 1, 2, 3, 4, 5. Number 23. Give examples of 3. Well, I'll just read them all down the line. Alkaline metals: lithium, sodium, potassium, rubidium, cesium, francium. Alkaline earth metals, period 2, or group 2 or 2A: beryllium, magnesium, calcium, strontium, barium, radium. Where am I? Transition metals, basically everything in that middle section. So chromium, cobalt, iron, nickel, copper, zinc, silver, gold. There's tons of them. Halogens, that's your fluorine, chlorine, bromine, iodine, astatine. And noble gases: helium, neon, argon, krypton, xenon, radon. 24. I know that these are all covalent because nitrogen and oxygen are both nonmetals. So we're going to name them using our Greek prefixes. So NO2 is nitrogen dioxide. The next one is dinitrogen dioxide. Then it's dinitrogen tetroxide. Then it's tetranitrogen pentoxide. Nitrogen trioxide. And the last one is nitrogen monoxide. Number 25. Write the total ionic equation and net ionic equation for the reaction between calcium chloride and sodium carbonate. That's from the White Lab. Okay. CaCl2 plus Na2CO3. I know the states here. Calcium chloride is going to be aqueous because these are both solutions. And that's going to yield CaCO3, that's solid, plus 2 NaCl, aqueous. Now this is just my regular balanced equation, it's neither one. By the way, if you don't know the states, this is what this is for. Okay, you look them all up, they're all there. Now for my total ionic equation, I'm basically splitting up all my aqueuses and accounting for all my ions. So, calcium 2 plus aqueous. I know that because this is aqueous, so that's aqueous. Plus 2 chloride ions, aqueous. Plus 2 sodium ions, aqueous. Plus 1 carbonate, aqueous. Yields CaCO3 solid. Keep your solids together. Plus 2 Na plus aqueous. Plus 2Cl minus aqueous. That's my total ionic equation. I'm looking for net here. So we're going to basically remove anything that is duplicated. So this, and this. So my net is just going to be calcium 2 plus, aqueous, plus carbonate, aqueous, yields CaCO3 3 solid. That's my net. 26. How many electrons can a single orbital hold? 2. The s holds 2. Each p orbital holds 2. So while there is like 2p6 or 3p6, that consists of 3p orbitals, each of which holds 2. Page 1 done. 27. Write the Lewis structure for the atom of Sb. That would be antimony. So that is in group 5A. I think that's got to be the first time we worked with antimony. 5A, so 5 valence electrons. What's my number here? This is 27. Let's see. Chlorine, 7 valence electrons. And nitrogen, 5 again. Oops. 1, 2, 3, 4, 5, like that. 28. What is meant by ionization energy? Ionization energy is the energy to ionize, or in other words, to turn an atom into an ion. Now, how do you turn an atom into an ion? You remove electrons from it. So basically, it's the energy required to remove an electron. And the trend we generally see is our metals on the left have low ionization energy because they are eager to lose electrons and form ions. The nonmetals on the right have very high ionization energy because they are not eager, again personifying them. It takes a lot of energy to remove their electrons because they're more stable when they gain electrons. So they have high energy, meaning it takes a lot to get it done. 29. The general shape of s and p orbitals. Imagine that's my nucleus. S orbitals are spheres. Okay? 1s, 2s, 3s. The p orbitals are what I call bow tie shape. I'm sure there's a better term for it, but there's no 1p, so you're not going to see anything like that. But the 2p looks like this. That's 2px, 2py, and the 2pz is coming directly at the camera and going right into the board. So sometimes I do like a dashed line. That's 2p. My 3p is, again, inside this. So that's 3px, 3py, and then 3pz in the board. 30. What's the difference between an atom and an ion? An atom has no charge because the protons equal the electrons. An ion has a charge because it has either gained or lost electrons. You wouldn't say it has gained or lost protons, because if you gain or lose protons, you just change the identity of the atom. 31. Briefly describe the difference between ionic and covalent bonding. Ionic bonding involves the transfer of electrons between two atoms. Covalent bonding is the sharing of electrons between two or more atoms. 32. Show the bonding in the molecules of H2O, H2O2, and NH3 using Lewis structures. Okay, H2O. First, I'm going to start with my O in the middle and my two H's. Now, I know from experience this one's going to be bent. I'm just used to drawing it like this. What I want to do is count how many electrons I need. So hydrogen each brings 1 to the table, so that's a total of 2. Oxygen brings 6, so I need 8. So next I'm going to draw my electron pairs. Now hydrogens are good, but oxygen needs 2 pairs here. So now oxygen satisfies the octet rule. Hydrogens are good with 2 each, meaning these 2. Count up everything, 2, 4, 6, 8, so this is correct. That's water. Next, H2O2. So H2 gives me 2 electrons, O2 gives me 12 electrons, so a total of 14. Alright, now this one's a little tricky, there's no real center, but what we're generally going to do is put our hydrogens on the ends. So I'm going to do my 2 O's in the middle with 2 H's sort of coming off the ends, because the hydrogens can't be in the middle. Okay, now I'm going to add my lone pairs to satisfy octet rules. Okay, so now my oxygens all have 8. And now I count. 2, 4, 6, 8, 10, 12, 14. Easy, no double bonds. So that's correct. Last one, NH3. Still on number 32. Well, nitrogen has 5 valence electrons. Each H brings 1, so that's a total of 3, so I have 8. Again, I believe this is going to be a nice easy one. So N now becomes my central atom. So that's my skeleton. To add to this, I need to put 2 here. Okay, now count them all up. 2, 4, 6, 8. This is correct. Number 33. What is meant by a polar molecule? Well, a polar molecule has basically one atom is more electronegative than the other, so it basically hogs the electrons. The actual definition is the electronegativity is between 0.4 and 2.0. 34. What is meant by electronegativity? It's a ranking of how well an element attracts electrons. So you can imagine metals have low electronegativity because they don't attract electrons, they want to give them up. And my nonmetals, especially those in the top right, have high electronegativity because they very much attract electrons. And again, that was number 34. Keep up my numbering. 35. Briefly describe the trend in electronegativity as you go down a group and across a period on the periodic table. Okay, so atomic or electronegativity. Down a group, let me aim this here. Going down a group, electronegativity drops. Electronegativity drops. That's because electronegativity is how well you attract electrons, and the thing that attracts the electrons is the nucleus, specifically the protons in the nucleus. So when the nucleus is very close to the outside, like in fluorine, like in lithium, like in beryllium, it's easier for it to attract electrons. However, down here in astatine, iodine, tellurium, yes, they want electrons to fill that valence shell, but the nucleus is so far away, and there's so many other electrons getting in the way that are actually repelling those outside electrons that it's harder for this to attract electrons. And down here, cesium is more stable when it loses an electron, so I like to say it wants to lose the electron, and it's very easy for it to do so because the nucleus is so far away. Let's see, the trend in atomic radius. So this is number 36. Down a group, atomic radius grows, and it grows greatly because every time we go from this to that, to that, to that, to that, we're adding a new s orbital, which is just a sphere. Same thing down here. This is, 2p, 3p, 4p, 5p, and those p orbitals are within that larger s. So radius grows down the group. Across a period, atomic radius shrinks because the largest you're going to get is the s orbital. If you look way back here, where did I have my drawing? So here, you can see that the p orbital's within the s. So as I fill up my p orbitals, I'm not adding to the size of the atom at all. And in fact, every time I add more, I'm also adding more protons in the nucleus. And what these protons do is they're able to grip the electrons and kind of compress everything in. So as I add more protons and more electrons, it kind of grips it tighter, so that's why it shrinks. And then when you drop down the next level, boom, we add a whole new s orbital. So that's why it grows going down. Let's see what number we're on. So 37. Based on the trend above, which element has the smallest atomic radius? Well, that's going to be helium. Which element has the largest? Francium. Until we discover the next one, number 119. 38. What is meant by a nonpolar covalent bond? What that means is there is no difference or a minimal difference in electronegativity between the two atoms that are bonding. So a classic example is something like O2. What's the electronegativity difference between these? Well, it's zero. They're both oxygen. They have the exact same pull on electrons. So this would be a nonpolar covalent bond. There are also examples where the difference is so similar that we treat it as if it's nonpolar. And you can actually look up the electronegativity. The actual definition is 0 to 0.4 is what we consider to be nonpolar. Next, 39. Write the formula for, this is all about naming, calcium carbonate, iron 2 nitrate, tin 4 sulfate. Let me plan this one out. So tin is tin SN? Tin, yes. So tin 4 is this. Sulfate is SO4 3-. Crisscross rule. So I'm going to have this 3 go down here and that 4 go down here. So it's going to be SN3. Now I need parentheses. SO4 4. Tin 4 sulfate. Next, copper 3 chloride. This one's a little easier. Copper with a 3 charge, so it's going to be 3 chlorines. Copper 3 chloride. Ammonium phosphate. Well, ammonium's NH4+. Phosphate is PO4 3-. So it's going to be parentheses NH4 3 PO4. And sodium acetate, NaC2H3O2. Number 40. What's the difference between an anion and a cation? Anion is negatively charged, cation is positively charged. Number 41. A 25-gram sample of water starts at 30 degrees Celsius and is heated until it completely boils away. How much heat was added to it? Well, we have our 5-step curve. We're starting here at 30 degrees. We have to heat it until it starts to boil, and then we're going to completely boil it away and end right here. So 2-step problem. Step 1, let's find the heat it took to bring that from 30 degrees up to 100. So Q equals mc2 delta T. Q equals the mass of the water, which is 25 grams, times C2, which is 4.18 joules per gram degree Celsius, times delta T. Well, it started at 30, it's got to go to 100, so it's going to be 70 degrees Celsius. I'm going to use my cheat sheet here for 41. This equals 7320 joules. Okay, so that's the heat it took just to bring it up to 100. Next, let's find how much it takes for the water to actually boil. New formula, Q equals M times LV. You might also know this as M times HV, heat of fusion or latent heat of fusion. Anyway, Q equals 25 grams times our other constant, 2260 joules per gram. Gram cancels gram. And this is going to equal 56,500. We add these together. You'll notice that it pretty much always takes a lot more energy to boil something than it does to bring it to a boil. Total 63,800 joules. That is my answer. Let's see. 42. What is an endothermic reaction? Well, endothermic means it absorbs heat. And how can you tell if it's endothermic? By its delta H value. If delta H is positive, it's endothermic. 43. Sort of the opposite. Exothermic means it gives off heat, and you can tell it's exothermic because delta H is going to be negative. 44. How is heat of reaction delta H calculated for a chemical reaction? Well, what you need to do is use your chart here. You look up the heat of formation of your products. Make sure you multiply it by the number of moles involved. Find that total. Do the same thing for your reactants, and then do the products minus reactants, and that will tell you the kilojoules. Let's see. Number 45. Alright, so the reaction is CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O gas. We're trying to find the heat of reaction. So what we're going to do is look up all the heats of formation of these and multiply them by the number of moles involved. CH4 is negative 74.9 kilojoules per mole times 1 mole. O2 is 0 because that's the natural state of oxygen, so times 2 is 0. CO2 gas is negative 393.5 kilojoules per mole times 1 mole. And for H2O gas, we have 2 moles of it, so each mole is negative 241.8. Multiply that by 2 moles. Moles cancel moles, and we get negative 483.6. Okay? What we now do is add these together. Gives us negative 877.1 kilojoules. Add these together, negative 74.9 kilojoules. This minus this gives us our answer. Very careful you don't mess that up. So negative 877.1 minus negative 74.8 or 0.9. Minus minus really just equals plus. If we work this out, we get negative 802.2 kilojoules. We know this is exothermic because that value is negative. Okay, this will be 46. In the example above, 62 grams of methane are burned. How much energy is produced? Well, in this one, we're looking for the ratio. So it's negative 802.2 kilojoules, or it's this many kilojoules released for every 1 mole of methane. So if I have more moles of methane, I'm going to get more energy released. So what we need to do is find how many moles of methane I actually have. So number 46. Make sure my numbers are right. Yep. So in 46, I have 62 grams of CH4. Convert that to moles by saying 1 mole over 16.04 grams. Gram cancels gram. Gives me 3.87 moles of CH4. We're going to use our ratio that we found. So it's this many moles times that many kilojoules per mole. Now I'm going to invert the sign here to really show that it's the quantity of kilojoules released. I'm not necessarily dealing with negative kilojoules at this point. But you could do a negative. Just flip your answer. Mole cancels mole. The answer we get is 3,100 joules. So that's the heat, not joules, kilojoules. Typo on my answer key. 3,100 kilojoules released. Okay. Number 47, again feeding off this problem. In the example above, 31,500 kilojoules of energy are released. How many moles of CO2 must have been released into the atmosphere? So it's the same kind of problem, except now instead of giving you the moles or the grams, I'm giving you the energy. So we're going to say 31,500 kilojoules times, going back here, 1 mole over negative 802.2. But again, it's just this is the quantity released. So you could make it negative, you'd end up with negative moles, just flip that around. But what I'm really looking to say is 1 mole of CH4 releases this many kilojoules. So I'm going to make that positive. Kilojoule cancels kilojoule, and the answer we get is 39.3 moles of CO2. Okay, I'm going to go ahead and stop this one here because I'm about falling asleep. So I'll make the next step.